Here's a problem on standing waves and organ pipes. Organ pipes produce sound, so the standing waves are in air, and they are longitudinal. So longitudinal, that means the air particles are going to be oscillating left and right. The pipe is emitting its lowest frequency note. Here they mean it's emitting the first harmonic. Instruments operate using harmonics. The resonance that occurs, or let's say the standing wave that's produced, is why we hear a loud noise from the organ. And so here they mean it is producing the first standing wave, F1. On the diagram, sketch a representation of the standing wave in the pipe. Okay, well, this is an open end, so the particles at the open end move really far left and right. This is an open end on the other side. So here as well, these particles enjoy maximum displacement. And between two antinodes, we have a node. So these particles, literally in the middle, they will not move at all. But we're not drawing particles. We're supposed to draw a sign shape to represent those displacements. So let's say that these particles here have been pushed really far to the right. They have a big positive displacement. These particles here have been pushed really far to the left. They have a big negative displacement. And these ones in the middle have not been moved at all. We would draw the wave like, let's try that again, like this. Big positive displacement, big negative, and zero. It's right in the middle. Now I'm going to take away these shapes and leave it like that. Label with the letter A the displacement antinodes. Look, I already did that. And I'm going to take away the N to avoid any confusion at all. Although I want to make sure this goes to the bottom. There we go. Okay, I'm done here and I'm done here. The length of the pipe in A is 1.5 meters. Another pipe that's closed at one end has the same F1. And show that this second pipe is 0.75 meters in length. Okay. If we consider the wave speed equation, we do not know the speed in either medium. But here's the thing we can do. We can assume that the speed is the same for both. And that's safe to do because both pipes have the same medium, air. So if they have the same frequency, F1, then they have the same wavelength, lambda 1. So now we can write if frequency is the same, so is lambda, the wavelength. So now let's go find lambda 1 for the first pipe. The first pipe is shown up above. You can look and say, well, hey, this length L of 1.5 contains half of a cycle. And rearranging, we get this. Or you can memorize the formula. For a pipe open at both ends, n lambda n equals 2L. We're looking at the first harmonic, and we get the same formula. When we do that work, we have to do it inside the box. Lambda 1 is 2 times the length, which is 1.5 for the first pipe. We get 3.0 meters. So that means lambda 1 is also 3.0 for the second pipe. But the second pipe is different. It's closed at one end. So we're not sure what this length is, L. We know that the first wave looks like this. And in this case, using the formula n lambda n equals 4L, we're talking about the first harmonic, lambda 1. And we know that this is the same as what we found before. So now we have to show this work in our box, in this box here. so that we get credit. So we say in the second pipe, lambda 1 is equal to 4L. And so 3 meters equals 4L, and L then is 3 over 4, which is 0.75 meters.